Hello everyone, welcome to iitiansgateclasses classes. In this video lecture, we will discuss GATE 2020 database solutions, right? So let's start with first question. So this is a 1 mark question, came in GATE 2020, right? Consider the relation database containing the following schema, right? Here there are three tables are given: catalog table, supplier table, and parts table, right? Then primary key of each table is indicated by underlining the constituent field, right? So where the underline, that is a primary key. See, now these two attributes are the primary key of catalog table. This single attribute is the primary key of supplier table. Similarly, this part number is the primary key of parts table. So what we have to do, we have to execute this query and find out how many tuple in the end or in the result will come. Now see, number of rows returned by the above SQL query. You have to tell. Now, if you try to run this query, first, if nested query is given or sub query is given, first we need to execute the sub query, then come to the main query. So this is your sub query, right? Then we need to run to the main query. So try to first execute this sub query and find out the average cost. From where? From the, and one more point, in the SQL query, the first thing from where we have to start the execution. First, we have to start from the from clause. First is the from, then the second is a where part, then third is the group by, and fourth one is the select. So select. So where we have to go directly from clause. In the from clause, only one relation or one table is given. So this catalog table is given. So now second is the where. In the where, what you have to see this part number is equal to P4. Okay, that part number is equal to P4, they're asking. So part number is P4. P4 is here is given. P4. Only two tuple in the catalog table. And then we have to do group by of P number. So only we have P4. So here two tuple will come. So mainly S2 P4 200 and S3 P4 250. Right? These two tuple will come from the sub query. Then go to the select. Only this one is left. Where what we have to do? The average cost. So here cost is there. We have to calculate the average of these two tuples. So what will be the average of these two tuples? 200 plus 250 divided by 2. It will be 225. That will be the average of this. So here the result of this subquery will be 225 will come, right? Now you know the subquery result is 225, right? So let's go to main query. Here first we have to go directly to from clause. In the from clause, two tables are there. It means we need to take cross product of these two tables. So in the catalog table, 9 tuples are there. In the supplier table, 3 tuples are there. So in the cross product, 19 to 3, 27 tuples will come in the cross product. But in the where condition, then go to where condition. In the where condition, two conditions are there: supplier number and catalog supplier number is required, and cost is greater than 225, right? So you know cost is greater than 225 in the catalog level. Better first find out which tuple which is the cost is greater than 225, right? This tuple, this one. This four tuple having cost is greater than 225. So this four tuple and this is are the three tuple, right? Better to take cross product of these four tuple into three, not all. It is easy to find out the result. So 12 tuples will be there. 4 into 3, 12 tuples will come after the cross product after applying this condition. And on top of that, we have to apply this condition, right? So in the cross product, what will come? Your attribute serial number, part number, cost from the catalog, then serial number from the supplier, as name from the supplier, and location from the supplier. Now here 12 tuples will come, right? Now we have to find out this supplier number, catalog supplier number, and supply number is equal to, if both are equal to, then that particular tuple will select, otherwise not, right? Now you know, here supply number S2, right? And this is S3, and this one is also S3, and this one is also S3. Now check, S2 tuple is there, S2 is there, yes, this one is there. So this tuple will be selected, right? This tuple will be selected. So supplier number and S name will be in the result. So in the result will be first S2, then name will be MS Balaji. This is first. Second, go to S3. Check in this. In S3, if you check this one here, yes, S3 is match. So this one is also selected, S3 and premium. Now go to S again, this one, the third one, S3. Yes, S3 is there. Again S3 and MS premium. Now go to another last tuple from the catalog, S3, and if you compare from the supplier, yes, S3, S3. This one is also there. So S3, MS premium. So this 4 tuple will come in the result. So distinct keyword is not there. So all 4 tuple will be selected. Yes, these 3 are the duplicate, but distinct keyword is not there. So we have to keep in the result. So in the result, 4 tuple will be returned by this SQL query. The answer is 4. Okay. Okay, let's start the second question. This is also a one-mark question. Which one of the following is used to represent the supporting many-to-one relationship of a weak entity set in the entity relationship diagram, ER diagram? So they're asking which of the following is used to represent the supporting many-to-one relationship, right? Many-to-one relationship of the weak entity. The diamond with double border, rectangle with double, oval with double and bold border, and oval that contain underlined identifier. Let's see, for the rectangle, let's go to the B first. Rectangle represent entity, and double border rectangle represent weak entity set, and this is entity set. And oval with double order, this one, right? This is a multi-valued attribute, right? And oval with underline, this is a attribute which is a key attribute. This one is a attribute which is a key attribute, right? The first one, the diamond with double border, this represent as a relationship. Your diamond represent as a relationship, right? Diamond represent a relationship. To support weak entity set, we need double border diamond. So this relationship supporting many-to-one relationship to the weak entity set. So if you see, this is one-to-many or many-to-one. If you see, this is called many-to-one relationship. This is your weak entity set. This is your weak relationship set, or you can say relationship, and this one is entity. So for the supporting relationship, we need diamond with double and bold border. Answer is A.
So let's see next question. This question is a 2 marks question. And this question comes from the normalization. Consider a relation table R that is in 3NF but not in BCNF. Which one of the following statement is true? So a relation R that is in 3NF but not is in BCNF. So 4 points are given, A, B, C, D. We have to tell which one of the following statement is true. Or in normalization, what we do, we remove the redundancy, like step by step. First step, 1NF, we remove some redundancy. Then 2NF, we reduce redundancy. Then 3NF, then BCNF. So ultimately, when we reach at BCNF level, it means there is 0% redundancy in the database, right? So that is our actually a goal, to reduce the redundancy. So they are asking a table which is in 3NF but not in BCNF. So which line represent this statement. R is a non-trivial functional dependency. X implies to A, where X is not a super key and A is a prime attribute. So X is a not a super key. It means this X in the left hand side is not a super key, means it is a maybe a prime attribute or maybe non-prime attribute. But if you see in the right hand side, they mention A is a prime attribute. If A is a prime attribute, means from the X we can generate A. It means and A is a prime attribute, so X also become prime attributes. Prime attribute, right? So prime attribute to prime attribute we are generating, right? Okay. So in this they are saying in that relation prime attribute to prime attribute functional dependency is there, right? Now check first point, check second B. R has non-trivial functional dependency. X implies to A, where X is not a super key and A is a non-prime attribute, and X is not a proper subset of any key, right? So it means this X is not a prime attribute itself. It's not a super key. It's also not a proper subset of any key. So X is a non-prime attribute, right? Implies to A, and A is also a non-prime attribute. So here the functional dependency is non-prime implies to non-prime. The third point, R has non-trivial functional dependency. X implies to A, where X is not a super key. Okay, X is not a super key, and A is a not prime attribute. A is a non-prime attribute, and X is a proper subset of some key. So X is a proper. It means this X is the prime attribute because is a proper subset of some key, but it is not a key, right? Is a prime attributes implies to A is non-prime, and this is a non-prime. So here prime to non-prime. And the third, last one D, a cell in R hold a set instead of atomic value. So this they are saying atomic value is not there in this cell. So it means this is an unnormalized form. So this is not a unnormalized. This is an unnormalized form. This line is wrong corresponding to this one. Now you know in 1NF each cell is an atomic value in the each cell. Second one, if partial dependency is there, then we say this is not a 2NF. We say it is not a 2NF because in 2NF we remove partial dependency. What is the meaning of partial dependency? Right? From the prime attribute we are generating non-prime. This one is a partial dependency. From the prime attribute we are generating non-prime. So here C represent the partial dependencies there. It means this is not a 2NF. This is only 1NF. Right? The third, you have transitivity dependency where non-prime to non-prime we can generate. That represent a transitivity dependency. So here this is a transitive dependency is there, but if in 3NF we remove the transitive dependency, but this is transitive dependency, so it means this is not a 3NF. This is not a 3NF. It means it is a 2NF possible, only 2NF, right? And now come to A. Here prime attribute to prime attributes. This prime attribute implies to prime attribute dependency exists only in BCNF, but not in 3NF, right? So this line can represent this is a 3NF relation, but not in BCNF. We are sure with that. So answer is A. Okay. Now let's see next question. This is a 2 marks question. And question comes from the transaction. Here schedule S is given, right? With transaction T1 and T2, right? Two transactions given in schedule S, and RX stand for read on data item X, WX stand for write on data item X. And how many data items in the transaction in the schedule? A is given, B is there, C is there, D is there. It means 4 data items are there in the transaction. 4 data items are there. And the key point here is all the data items are independent to each other. So from the each data item we have to look, right? And what we need to do, which one of the following schedule is conflict equivalent to the above schedule? We have to find out these 4 schedules are given, A, B, C, D, 4 schedules are given. Which schedule is conflict equivalent schedule to the above schedule S? Let's suppose that S. And conflict equivalent means when we don't swap the conflict operation. When we don't swap the conflict operation. And what are the conflict operation? Here, read and write is a conflict operation, write and read is a conflict operation, and read, write and write is a conflict operation. These are the conflict operation, right? So when we don't swap, and read and write means from different transaction. It means this is a T1, then T2. This is T2, then T1, whatever the transaction order, right? We don't swap the conflict operation. Now check, first check with the A. First check with the A. So here, on data item A, only read operation is there. Any other A? No, there is no other A. So only one operation is there. So there is no chance of conflict, right? So it means on data item A, this S schedule is equivalent to A, B, C, D, corresponding to A. Now check with B data item. Now check with B. So see how many B data item operations are there. These are the B item operation is there, right? This one, and this one, right? Now check this schedule S is equivalent to A, B, C, D, what? Corresponding to B data item. Now this is B data item, this one is B data item, and this is B data item. Now you see R and B, one conflict operation is there. Order is same, corresponding to schedule S. Now check right and right, this second conflict operation is there. Order is same, right? So it means this S is equivalent to A. Now check with B. Now check with B schedule. This is your B, here B, B. Now this is write to read. We swap here, corresponding to schedule S, right? Now T1 is executing first, then T2, which is wrong. But in the schedule S, T2 first, then T1. Similarly for second operation also, right? So this can't be. B schedule is not equal to schedule S corresponding to B data item. So B not possible. Now check with C. If you check with C, this one here. Yes, order is same. So this is equal to C also. And check with this one. Here both are given, and here one. Yes, this one is also same, corresponding to. So this B schedule, this B on B data item, from the B data item, what we are getting, schedule S is equivalent to A, C, D. B is not there. So now further on, there is no need to check. There is no need to check B schedule. No need to check from here. Now come to C data item. Come to C data item. Here in the C data item, what operations are there? This is C operation, C data item operation is there, this one. So that is a conflict. First, we need to execute T1, then T2. T1, then T2, right? Now C in the A, order is same or not? Yes, this is C, and this one is C. Order is same. So it means S is equal to A. Okay, now check with the C. Yes, order is same. Now this is also equal to C, right? Now check with this one. No, here WC is coming first and compared to RC, which is T2, then T1, which is wrong. We want T1, then T2. So D is not possible, right? So here this option is also gone. Now check with D data item. Check with D data item. If we check with D data item, you need to see how many operations of D data item. This is write operation, and this is read operation. So order of this is T2, then T1. T2, then T1, right? Now check with A and D option, because B and D schedule is gone. Check with A. Here T2 RD, then WD. Yes, this is equal to A. And check with C operation. WD is first, then RD, which is a opposite to schedule S. So B is not possible, C is not possible. This is also gone. So which schedule is common? A is here, A is here, A is here, A is here, right? So in the all A, B, C, D data item, A schedule is common. So answer is A. Yes, this A schedule is conflict equal to schedule S, right? Let's see next question. This is 2 marks question also. This question come from B plus tree. Consider a database implemented using B plus tree for the file indexing and installed on the disk drive, right? So that index file in the disk drive with block size of 4 KB. So your block size is 4 KB, 4 KB. So it means 4096 bytes. And the size of the tree and this pointer is 8 bytes. So your tree pointer is 8 byte. Assume that database has 1 million record. So how many records are there? 1 million. So number of database records, number of DB records, 10⁻⁶, right? And also assume that no node of the B plus tree and no record are present initially. So in the main memory, nothing is there initially. Consider that each record fit into one disk block. The number of disk access required to retrieve any record in the database is. So the main thing is each record fit in the one disk block, and number of disk access required, minimum number of disk access required to retrieve any record in the database we need to find out. If minimum number of disk access required, it means maximum fill is required in the blocks. Maximum records we need to fill in the blocks, means index records we need to fill in the blocks. And your search key is 12 byte is given. This is given 4 KB and 8 byte, right? So first of all, if one block is there, right? If one block, let's suppose this one block is, how many search key we can insert in the one block, we need to find out. And this is a B plus tree, so the internal node, you know the internal node function. Let's suppose P is the order. P is the order of the block P, right? And this one P is the order, and the size, your size of the tree pointer is 8, right? 8 is the size of the tree pointer. Plus, if search key, the order P means number of pointers, right? Number of tree pointers, P means, right? So it means number of search key will be in the block P minus 1, right? P minus 1 into 12. And there is no record pointer in the internal node. You know that in the B plus tree, right? And the size of the block is 4096. So what will be the order? If you calculate the order, it will be 25 point something. So around, so P will be 205. That number of tree pointer possible in the B plus tree block. So it means here your search key. So these are the tree pointers. How many? 205 maximum possible in one block, right? Now the minimum number of disk access required to retrieve any record in the database we need to find out. So it means, what does mean? Here this is your database, 10⁶ million records are there. Here this is your level 1, then level 2, then level 3, then level up to go on like this, up until we reach only in the last one block. In the last one block we reach. When we reach in the last one block, okay, that's up to that possible. So from that we can say that number of block is required to access a record, means this is 1, 2, 3, and the last block from the database itself, right? So we need to find out how many blocks are required to access the record. Right now, you know, we can draw the diagram. We can draw the table for the level. This is your level table, and nodes possible on that level, then keys and pointer, right? So on level 1, only one node is there. In the tree on level 1, only one node is there, right? How many keys possible? You know, pointer 205 pointer possible. So it means keys are -1. You can do 2 raised to 204. That number of keys, search key possible in one node, right? In the level 2, now if this is level 1, so how many maximum tree pointer? 205. So it means 205 nodes possible. 205 nodes will be there maximum, right? And in each node, how many keys? 204. So how many nodes? 205 into 204 keys on level 2. On level 2. This is your level 2. This is your level 1, right? And now how many pointers? 205 nodes, and each node 205 pointers, right? This will be the on level. And if you now go to next level, how many nodes third level, it will be 205 into 205, right? The same number, that number of nodes in the level 3, and each node containing 204 keys. So 205 number of nodes into each node, that number of keys, right? And how many pointers for the next level? 3. Now they are saying number of records are 10 raised to power 6 in the DB. So this number of keys can represent 10 raised to power 6. Yes, this is near about 8.5 into 10 raised to power 6. We can save. So how many database? Okay, this level is sufficient. Up to 3 level is sufficient. We can store all the information at level 3, right? So 3 level means 3 block access is required from the index area. From the index area, 3 block is required to reach the record, plus 1 block where we have to reach to the database, right? So this is 1 block from here, 1 block from here, 1 block from here, 3 block from the index area, index 5, right? And 1 block from the database where the actual record is there, 1 block. So it means 3 plus 1 is equal to 4 block access is required to access the record or retrieve record. 4. Answer will be 4.